Hello viewers, welcome back to our series of lectures on NMR spectroscopy. In today's session we will continue our interpretation of NMR spectra. In the previous session we started with this, today we will continue with that. The session is planned as follows, that is, to begin with we will briefly review what we did in the previous session. Thereafter we will recall the strategy for the interpretation of NMR spectra which we evolved in the previous session, and then thereafter we will take up certain examples of different NMR spectra and try to interpret them and in terms of the structure of the molecules there, and towards the end we will sum up what we do today. Okay. Let's briefly review what we did in the previous session. In the previous session we recalled structure spectrum correlations which we established little earlier than that. So, having recalled structure spectral correlations, we devised a strategy for solving structural problems based on NMR spectra, and then thereafter we used that strategy to solve certain problems based on NMR spectra. Now, today we will continue from there on, and to continue we will try to recall the strategy which we evolved in the previous session, and that basis then we will take up the examples from here. Okay. If you remember, the strategy was as follows, that in the very first step what we do is we recall the strategy what we developed in the previous session. In the strategy you remember that in the very first step what we do is we calculate HDI, that is hydrogen deficiency index, on the basis of molecular formula of the compound for which the NMR spectra is given to us. And that actually indicates us about the kind of unsaturation or rings present in the molecule under consideration there. In the second step we match the integration peak areas with the number of protons in the molecular formula, that we see that what is the integration pattern there, and then we try to see that how do they correlate with the number of protons in the molecular formula. Then the next step actually we take care of the splitting patterns. We try to locate that what are the splitting patterns of different signals there that actually are indicative of the number of neighboring protons. So, that is the step number 3. Then the next step what we do is we look for characteristic patterns if there are any, like for ethyl group we know that you will get 2 signals there, 1 quartet, 1 triplet, and then that pattern we have learned about earlier, or maybe a tertiary butyl group we know that what kind of pattern to expect, or maybe some kind of a isobutyl group. So, we know that some typical patterns which we have discussed earlier. So, those patterns we should keep in mind, and suppose the patterns are there in the spectra, that give us a straight away clue to what to look forward to. So, that gives an indication about some part of the molecule under consideration. The next step what we do is we try to identify what are the possible types of protons. We have seen that how many the number of signals tells us how many different types of protons are there, but which proton, which signal is coming because of which type of proton, what kind of functionality is involved in that, or whether they are aliphatic protons or aromatic protons. So, those things we try to identify, and for that the following scheme becomes very handy here. If you remember that, you please pay attention to this once again, that is typically the aliphatic protons come from somewhere from 0 to 2 ppm, that is CH3, RCH3, RCH2. So, they are typically are observed somewhere over here from 0 to 2 ppm. This guide is very useful here. And then if you have got some aliphatic protons which are linked to some kind of a electron withdrawing, say a carbonyl group or an aromatic group or some other electron withdrawing group like sulfur or nitrogen is there. So, NCH2, NCH3, ArCH2. So, those kind of protons will be observed somewhere from about 2 to 3 ppm. So, they are the typical ranges which we discussed earlier. We are trying to recall them here so that we can make use of when trying to answer the questions we are going to take up today. Then this again is important here, that is the protons, like typically where a CH2 is attached directly to an oxygen or to an electronegative atom like X. They typically come from 3 to 5 ppm depending on what is the electronegativity of the atom attached to that. And then going further, this is the typical region about 5.5 to 6.5 or so, where we look forward to the unsaturated protons there. And then 7 to 8 we all know very well, it is the range for aromatic protons. Then around 9 to 10 we look for the aldehydic protons, and thereon from 10 onwards, 10 to 12 or so, we look forward to for acidic protons. Carboxylic acids are observed somewhere in this range. And typically if you got OH or NH, they come anywhere from 0 to 5 ppm or so, because the signals are single proton signals, they are easy to locate over there. So, this step 5 is very, very crucial, because that gives us an idea about what kind of protons are there in the molecule there. Then in the next step what we do is, we see that by identifying different types of protons, are we able to account for all the protons in the molecule? So, if not, then we have to see for the missing protons there. If yes, then what do is, we try to assemble the structural elements, whatever we identified by this step, we try to arrange them together and to work out some kind of a tentative structure for the molecule, because that is still tentative, we are not sure about the molecule as yet. Then what do we do next is, we revisit the spectrum, that we try to correlate the structure we are trying to kind of propose here and the spectrum, and try to see that does the spectra account for all the protons we are trying to look forward to, or something more is required. So, that is the step number 8. So, with these 8 steps, we should be in a position to solve a problem based on the NMR spectrum. Now, let us take up some examples of NMR spectra and try to interpret them, and then see that how do we make use of this strategy which we just try to recall for ourselves. Let us take the first example. This is the NMR spectrum for a molecule whose molecular formula is given to us as C7H14O. And as we remember, the first step is to work out the HDI. HDI for this can be worked out. We know that when you are trying to work out HDI, we do not consider oxygen over there. So, the HDI will be worked out only for C7H14. And for this, I am not getting into how to do that, I am sure that you know it by now. When you work out HDI, it comes out to be 1. That means this molecule contains either a double bond or a ring. So, that is the kind of information I get from this very data, that HDI happens to be 1. Then the next thing we look forward to is the number of signals here. We see that the number of signals are 3. This is one signal, second and third one. That means there are 3 types of protons in the molecule there. So, second information. The next thing is, we look for the integration ratio, which is very clearly mentioned on the spectra itself, that there are the 3 signals over there for 2 protons, 3 protons and 9 protons respectively. Total it adds to give me 14 protons, which are there in the molecular formula over there. So, that is very, very straightforward. Let us move further and look at the signals over there. So, the first signal which we look forward to is, that is a 9 proton singlet around 1 ppm. Around 1 ppm, that indicates that is typical of an aliphatic methyl group there. But since there are 9 protons there, that suggests that we are looking for about 3 methyl groups, and since it is a singlet, then all of them have no neighbors with them, and that is a typical possibility when these 3 methyl groups are attached to a carbon atom to form a tertiary butyl group. So, these 9 proton most likely are likely to be because of the tertiary butyl group there. Another signal, the second signal we have, which is important for us, is a 2 proton singlet around 2.3 ppm. Now, there are 2-3 things to look forward to here. Firstly, 2 proton signal. 2 proton means it is a CH2. Second, there is a singlet, that means there is no neighbor. Thirdly, we got about 2.3 ppm, that means this methylene group there, CH2 group, is attached to some kind of an electronegative group or an atom or an electron withdrawing group, and we suspect it to be a carbonyl group, something like this. Maybe we have got a CH2 group attached to a carbonyl. There is a possibility we propose for the location of this particular signal over there. Third signal we have is a 3 proton singlet at 2.1 ppm. Similar to what we have here is, again 3 proton means there is a methyl group there, singlet means no neighbors, and 2.1 ppm some kind of a electron withdrawing group in the neighborhood. This could be the possibility there. So, we have identified 3 different fragments on the basis of the 3 signals we have found in the NMR spectra here. Let us try to put them together. To put them together, what we get is, we get some kind of a tentative structure of this kind. That means, this is one fragment we had, this was the second fragment we had, this is the third fragment we have. So, these 3 fragments when we link together, we get the following structure. And let us see that how does it relate with the spectra we have obtained here. Now, if this is the spectrum structure of the molecule, then where do we expect the signals? This kind of assignment let us try to take up now. These methyl groups are accounting for that signal at 2.1 ppm, because there are 3 protons, singlet will come there, and since attached to a carbonyl group, we will locate it at around 2.1 ppm. This will come around 2.3 ppm, again a singlet because there is no neighbor over there, and that is what we have experimentally observed there. And since because of the carbonyl group in the neighborhood, this will come at a low field there around 2.3 ppm, and this typical tertiary butyl group is expected at 1.01 ppm. That is where it is observed. So, by this we can work out that the NMR spectra given to us belongs to this particular molecule over there, and we know that this corresponds to the molecular formula given to us. In this whole analysis, we computed initially that there is HDI of 1, so there is one double bond in the form of carbonyl group there. So, we can see that by using the strategy we have evolved, we are able to kind of assign the structure to the molecule on the basis of the NMR spectra given to us. Let us move on, go to the next example. Now, this again is very simple spectra here, and the molecular formula is given to us C8H10O2, and here again typically, as we have been doing all these times, we compute the HDI. HDI for this will come out to be 4, because we will not consider oxygen here. So, we just take C8H10 and compute the HDI. It comes out to be 4. That indicates that either there are 4 double bonds in the molecule, or there could be some combination of rings and double bonds, maybe 1 ring and 3 double bonds, and so on and so forth. Different possibilities are there. We will come to that as we proceed. The next information we have got from the spectrum is that there are 2 signals. That means there are 2 types of protons. Fair enough. Next, we look into the integration ratios. If you compare the integration ratios here, this and this, they are in the ratio of about 4 to 6. 4 to 6 means, that is, if you add 4 and 6, that makes me 10, and then there are 10 protons there. So, that straight away tells me that this signal is for 4 protons and this signal is for the 6 protons over there. So, that is what information we get from the integration pattern there. Now, we have got two signals there, that means there are 2 types of protons, and both of them happen to be singlets. Let us analyze the first singlet at about 6.8 ppm, and that is for 4 protons. So, 4 proton singlet at 6.8 ppm, 3 informations there. Let us try to see what do they indicate to us. First one, location at 6.8 ppm, typical of aromatic protons. So, we are looking for that means there is a possibility of an aromatic ring in the molecule, that is number 1. And then since there are 4 protons of an aromatic ring, that suggests that if you have got benzene as an aromatic ring over there, which is most likely, so that benzene happens to be disubstituted. Disubstituted, that is why there are only 4 protons left there, 2 protons have got into substitution there. The third information is that we have got a singlet here. Singlet suggests that this has to be symmetric in nature, because if it is not symmetric, I will not get a singlet, I will get more than 1 signals there. So, these 3 bits of information put together suggest that I have the fragment which is causing this signal here is nothing but para disubstituted benzene, that is C6H4 as the fragment there. That is how do we show it here. So, this corresponds to these 3 observations what we had here. Let us move to the second signal. Second signal is a 6 proton singlet at around 3.8 ppm. This is very interesting. Now, there are again 3 things there. One, the number of protons, 6, fine. Singlet means no neighbor, and then location 3.8. I think that is where we should start with. 3.8 is a very characteristic location for O-methyl group, because this position tells me that these signals are nothing but because of the O-methyl group there. O-methyl comes around 3.8 ppm. It is very, very characteristic there. Now, but O-methyl means there should be only 3 protons there, but I have got 6 protons. That suggests that probably we have got 2 O-methyl groups there which are contributing to this signal over there. Okay, if that be so, our fragment now comes out to be 2 OCH3s put together can give me O2 C2H6. So, there are 2 fragments, one fragment is C6H4 and second fragment is O2 C2H6. I put the 2 together. When I put the 2 together, these fragments add to give me C8H10O2, and that is my molecular formula. That means I have been able to account for both the components, that means I am able to account for the molecular formula in terms of the fragments I have been able to identify. If that be so, what do I do next? what do I do next is I take these fragments and put them together into some kind of a tentative structure, and the tentative structure which comes out to be obviously nothing but the following structure here. Now, when I do this, the next step obviously is for me to assign that where do I assign the signals there, then which is very straightforward. So, these two O methyls there, they will come at 3.8 ppm, that is where they are observed, and these 4 protons 1, 2, 3, 4, because of this symmetry of the molecule, they all will come together at one single location, that happens to be 6.8 ppm. That is what is observed there, and that is the kind of structure we have for the molecule. And we had computed that HDI of 4, that also is accounted for here. So, what do we have here? We got a benzene ring. A benzene ring has got 3 double bonds, 1, 2, 3, and also it is a ring. So, 3 double bonds and ring put together, that accounts for the HDI of 4. Typically, that is how do we account for benzene rings there. Let us move further and take up yet another example. Example number 3. The molecular formula for the compound whose spectrum is given to us is C4H8O2. And typically, as we have been doing, we start by computing HDI, and that comes out to be 1. That indicates that in the molecule I have got either a double bond or a ring. The number of signals are 1, 2, 3, which is very, very obvious here. And if we try to look at the integration ratio which has been worked out and shown on the spectrum itself, that there are 3 signals and they correspond for 3, 2 and 3 protons respectively there, and 3 plus 2 is 5 plus 3 is 8, and that is what we have in the molecular formula. So, this integration ratio satisfies, it kind of agrees with the number of protons there in the molecular formula there. Let us move further and try to look at what are the signals there and what do they indicate to us. First signal we see is the 3 proton triplet at about 1.2 ppm. What does it indicate? 3 protons typically of a methyl group. A triplet indicates that there are 2 neighboring protons there, and location is 1.2, which is typical of aliphatic protons. So, this signal is likely for these 3 protons attached to a methylene group over there. Because of this methylene group, I am getting a triplet here. That is one signal we got. The second signal is at around 2.4 ppm. It is a 2 proton quartet. So, 2 proton methylene group, quartet means there are 3 neighbors there, and location is interesting here, that is 2.4 ppm. That indicates that we are looking for some kind of a methylene group which has got 3 neighbors, and also methylene group is linked to some kind of electronegative atom or an electron withdrawing group. That means, this is the methylene group which is causing this signal over there. There are 3 neighbors which are making the signal as a quartet, and there is some group there which is making this position go to 2.4 ppm. Had this group not been there, I would have expected this also to be somewhere around 1.2 ppm. What is this group? Let us try to anticipate that. Maybe a carbonyl group, because that is typically, we know that this location of 2.2 to 2.4 or so is because of a methylene group attached to either an aromatic ring or to a carbonyl group, or maybe a nitrogen or an oxygen, and so on and so forth. So, this we suspect it to be a carbonyl group there, or maybe an aromatic ring, possibilities there. Now, next what we look forward to is that in this spectrum there is a typical pattern. A typical pattern is of the ethyl group there, because there is a 3 proton triplet and 2 proton quartet. That is typical of ethyl groups there, and we see it that in our spectrum also. What you have got is there is a 3 proton triplet and 2 proton quartet. So, that indicates that this molecule contains an ethyl group. The third signal what we have is there is a 3 proton singlet at 3.8 ppm. 3.8 again, I am sure that you got suspicious of this to be a O-methyl group there. So, by this what we have is we got 3 fragments here. One possibility, that means one is your methyl group there, and then a methylene, and also we got a pattern of this kind. That means we have a ethyl group somewhere in the molecule there. That is number 1. And number 2, we have got something like OCH3. Let us see how do we go further. Now, if I look at this, what do I have? I have got C2H5, that is ethyl group there, OCH3, and of course a carbonyl group which we expected, because to account for the location of our methylene protons there. Okay. So, they all add up to give me C4 H8O2. And if I combine all these fragments there, what do I get? This is one possible way of combining them. That is, we have got a CH3CH2, that is a ethyl group there, then of course a carbonyl which is causing this methylene to go downfield, and then of course we have got a OCH3 which is giving me signal at 3.8 ppm. This beta structure, let me try to put assignments over there. This signal is at 1.2 ppm, typical of a methyl group, and that is an aliphatic proton which will come around 1 ppm or so, nothing unusual about it. Then second signal is we are getting at this methylene group, this is coming at 2.4 ppm and is coming as a quadrate because of these three neighbors there, and location of 2.4 can be accounted for in terms of its being in the neighborhood of a carbonyl group which is making it go downfield there. And the third signal is very obvious, that is we got a methyl group, a singlet coming at 3.8 ppm, that is suggestive of OCH3. So, it is very simple molecule which we have been dealing with. So, that is the structure of the molecule we have. Let us move further, take up yet another example. Now, in this case the molecular formula is C9H10O, and there are about 1, 2, 3, 4 signals in this. So, it is slightly more involved problem than the previous problems there, but we will go in the same way. We start by computing HDI. HDI comes out to be 4, which again we know that it means either there are 4 double bonds or maybe some combination of double bonds and a ring over there. Number of signals is 4, that means there are 4 different types of protons, and if you see the location, these 2 signals here for 2 proton and 3 proton, they are typical aliphatic protons there, and these 2 signals somewhere around beyond 7 ppm, they are suggestive of aromatic protons there. So, there are 4 signals in total, 2 are aromatic, 2 are aliphatic. Let us move further. Now, look at the integration ratio that has been solved and shown on the spectrum, that the signals are for 2, 3, 2 and 3 protons respectively. Now, let us analyze the signals what we get for aliphatic protons. In the aliphatic protons, there are 2 signals. The first one is at about 1.2 ppm, there is a 3 proton triplet. What does it indicate? This indicates that the 3 proton means it is a methyl group, a triplet means there are 2 neighbors, and location of 1.2 ppm, which is very, very straightforward, that it is a aliphatic proton, and we suspect it to be a CH3 attached to some CH2, a methylene group, which is causing this signal over there. Second is we got a 2 proton quadrate at 3 ppm. This is again very, very interesting, because we got a 2 proton quadrate, methylene group, 3 neighbors there, and location is 3 ppm. So, that indicates that this methylene group with 3 neighboring protons is linked with some kind of electronegative atom or an electron withdrawing group there. That means, this is similar to what we had in the previous case there. That is, this methylene group which is causing this signal at 3 ppm is linked with some group which is electron withdrawing or electronegative, and again we suspect it to be a carbonyl group there. So far probably we can work out, because this again is some kind of a typical indication, 3 proton triplet and 2 proton quadrate, that there is some kind of a ethyl group in the molecule. So, that is the structure we propose at this stage, that this fragment happens to be CH3CH2, a carbonyl group over there. Let us move on to analyzing the aromatic part of the spectrum. And aromatic part of spectrum, if you look at what do we see, that there are 2 signals there. That is very, very important, please pay attention to this. There are 2 signals, one signal is for 2 protons at 8 ppm and second signal is for 3 protons at 7.5 ppm. What does it mean? If we add these 2 together, 2 proton plus 3 proton adds up to give me 5 protons. That means it is a monosubstituted benzene ring, because we are getting signals for 5 protons there. But if it is just a monosubstituted benzene, probably all of them should come together, all the 5 protons, but we are getting them into 2 parts. One is for 2 protons, one is for 3 protons. That indicates there is some kind of a anisotropic substituent to the benzene ring there. That means this is one possibility we have. We have got a benzene ring and it has got a substitution on this, and that substitution happens to be maybe a carbonyl group, because this carbonyl group has an anisotropic effect. And what will happen is, because of this anisotropic effect, this carbonyl group, these protons, the 2 protons which are ortho to this carbonyl group there, to this substitution over here, they will come at a low position there. That is what we are getting here. And the rest of the 3 protons which are farther from this carbonyl group, or the anisotropic effect of this, probably will come at the typical position of about 7.5 ppm. That is what we propose at this stage. Okay, let's assume that the two fragments we have proposed happen to be true. Then let's try to work out the structure there. If I combine the two fragments, I get the following. I can propose the following structure for the molecule whose spectra we are trying to analyze there. So there is a benzene ring, there is a carbonyl group, and there is a ethyl group over there. And as we have been doing so far, we will now try to do assignments to this. This methyl group typically is at 1.2 ppm. That's where we expect. This will come at 3 ppm. It will come as a quadrate because of the 3 protons neighbor here, and of course a neighborhood we have got a carbonyl group. That's why this location is about 3 ppm. Then these 2 protons which are ortho to this substitution here will come at 8 ppm, and these 3 protons will come at 7.5 ppm, and that is what we observed. The molecule which we are proposing as a tentative structure happens to be the molecule whose spectra we are trying to deal with here. Okay, I am sure that by now we know how do we go about, what is the strategy we proposed earlier, and then how do we make use of strategy, and we are able to work out the structure of in a reasonably good details over there. Let us move further and take up yet another example here. Now, this is a very simple spectrum, but a larger molecule there. It is C9H10O2, HDI again 4. So, 4 double bonds or some combination of double bonds and aromatic double bonds and a ring there, and in a number of signals 3. That means there are 3 different types of protons which are very characteristics in this case, and out of these 3 signals, 2 of them happen to be in the aliphatic range there, say from 0 to about 5 ppm or so, and this is a typical about 7 point something is the aromatic proton there. So, there is one aromatic signal and there are 2 aliphatic signals there. Let us talk about the signals now. So, we got a 3 proton singlet at 2.1 ppm, which indicates that we have a methyl group which is linked with an electronegative atom or some kind of electron withdrawing group. So, that is what we interpret from this signal there, and this could possibly be a carbonyl group or an aromatic ring. So, there are 2 possibilities which can make this signal go downfield like that, as we have observed. And if it happens to be a carbonyl group, probably our fragment now is C2H3O. Okay. Let us go to the next signal there. The next signal is at this is a 2 proton singlet at about 5.2 ppm. This is very important. Now, what does this indicate? This indicates there is a methylene group with electron withdrawing methylene group attached with a electron withdrawing group, or maybe more than one group is involved in that. So, we have got CH2 attached to maybe a group there, another group could be on this side, because I am suspecting this to be so because the location is highly downfield, 5.2 ppm. If there is only one group involved there, or maybe as we have been observing about 2.1 to 2.4 or 2.5 ppm, or if it is directly linked to oxygen, maybe about 3.8 ppm, but now I am getting is 5.2 ppm, which is extremely downfield. That indicates maybe there are more than one electron withdrawing groups attached to this methylene group there. Let us go into the next signal, that is the aromatic protons. I am getting 5 proton singlet at 7.3, which is very straightforward. It is a monosubstituted benzene ring there. Now, let us add the fragments we have identified so far. Fragments are C2H3O, the initial fragment we identified, that is CH3CO. Then say another fragment we identified is 6H5. Then we had a CH2 there. If we add them together, we get C9H10O. We are short of an oxygen atom. We have been able to account for only one oxygen so far. Second oxygen we have to yet account for. That's where we go back to the spectrum and see that the chemical shift position of methylene group at 5.2, that indicates it to be linked directly to an oxygen atom as well, besides our electron withdrawing group as we have proposed earlier. So, the fragment is not just CH2, it is OCH2. If we have got OCH2 here, and then if we add O here, we will be able to account for the molecular formula what we have for the molecule given to us. Now if we combine the fragments, so what do we get? This is my monosubstituted benzene ring there. This is CH2 attached to O, that is OCH2, and this is CH3CO. So, all put together, that is the structure I propose for the molecule there. Let us take up the assignments now. This methyl group will come at about 2.1 ppm because of the fact that it is in the neighborhood of a carbonyl group. Because of the anisotropic effect of this carbonyl, this will come at 2.1 ppm, which is slightly downfield from the typical position there. And this methylene will come at around 5.2 ppm for the fact that it is attached to two things. One, directly linked to an oxygen atom, and also secondly, it is linked to a benzene ring, which makes it go downfield, further downfield over there. And thirdly, all these aromatic protons will come at about 7.4 ppm as a singlet over there, the typical aromatic location for that. This molecule happens to be benzyl acetate. I think I am sure that by now we know that how to put the strategy to use to decipher the structure of molecules on the basis of their NMR spectra. Okay, let's sum up what you have done today. What you have done today, we started by reviewing the contents of the previous session, and then thereafter we recalled the strategy for interpretation of NMR spectra. We talked about all the points, the sequence of points, how to follow that, and then we have taken certain examples and interpreted the NMR spectra of some simple molecules to decipher their structure. With that, we come to the conclusion of this session on NMR spectral interpretation. Thank you.